Alright, so we're going to do some PKS problems today. So the first thing that I want to show you is the problems that we're going to do, and then we're going to go over some of the ways to think about them. So this is number 3 from the practice homework, and you can see that it is asking us to predict the structure of natural product based on the following domains of this polyketide synthase. And so basically it lays out the different enzymatic domains you're going to have in this protein that will biosynthesize some kind of natural product, polyketide, at the end. And then we'll also be able to do this backwards, where instead of giving the domain organization, we're going to work on figuring out what the domain organization is by using a natural product. So this is methymycin, and that's one that we'll go over. So I'll leave the rapamycin one for you. That takes a lot longer, but if you have any questions, feel free to shoot me an email. Okay, so before we do PKS assembly line stuff, I'd like to review some FAS stuff. Alright, so for fatty acid, biosynthesis. Alright, so I apologize for my handwriting now. This is not easy for me, and I have bad handwriting as it is. So, alright, anyway, so in FAS, basically what we're going to be doing is extending things by 2 carbons at a time and then reducing them. And so the first thing you're going to have that starts FAS is you're going to have an ACP. This ACP has an SH on it. Alright, and so an enzyme called the malonyl-CoA acyltransferase. And so I usually call it an MAT, but the way you'll think about this in PKS is this is an AT, it's an acyltransferase. It's malonyl-CoA acyltransferase for FAS because FAS uses malonyl-CoA. Alright, so in this case, you'll have a molecule of malonyl-CoA, and we'll load this ACP. So now you're going to have an ACP with malonyl on it. So it'll be malonyl. All right. And so fatty acid biosynthesis is really going to be a process where it's an iterative condensation. But once you have this guy, this is going to be your extender unit for all of your cycles. All right, and so this was what's going to drive these reactions. So you have this this beta keto acid here, which is really prone to decarboxylation, and you can use that as a thermodynamic driving force to form carbon-carbon bonds, right? So for the first step in fatty acid biosynthesis, you're going to have acetyl-CoA. And you'll have a ketosynthase. And so what this ketosynthase is going to do is catalyze the condensation of these. I'm not going to go over the mechanism here, but basically you're going to do kind of a Claisen condensation, and so you're going to decarboxylate, and in doing so you'll free up these electrons to come and attack, and then they'll of course come back down and then kick out your CoA. Alright, so in that case, what you're going to get is what we call a beta keto ACP. Oops. I'll draw our ACP again. Alright, cool. So this is what you're left with, and of course you're gonna lose CO2. And like I said, this is like the thermodynamic driving force. It's Putting a CO2 back on requires ATP, so once you form this carbon bond and lose CO2, it's kind of trapped, and then you've made your carbon bond. So let's go ahead and do a numbering system here. So one, two. All right. Here, let's do a different color so we can keep track of it. So this is carbon 1, and this is carbon 2. All right. And then let's go ahead and say that. What's the best way to do this? Say it's 3 and 4. And so what we have here is 3, 4, 1, 2. Now, that might be confusing for you right now, but we'll just see if that works for this video. If not, I'll think of a better way to explain it. All right, so once you have this beta keto group, you're going to enter a cycle of reductions. And the first reduction that you're going to have is going to be done by a keto reductase. So it's a KR, it's a keto reductase, and it's going to use NADPH, and this is going to be a source of hydride, right? So that will come in and it's going to reduce this guy, pick up a proton. Alrighty. So once you have that, apparently smaller ACP, S, OH. So now you have this guy, so this is going to be beta hydroxy acyl ACP. It's going to continue. All right, so this next one is going to be the dehydration, right? So you have some protons here. And these can be removed. So you'll have like a base, and this is an enzyme called a dehydratase, so DH. And this base can grab this guy and just do your general kind of E2 style elimination. And then you will form an alpha beta unsaturated ketone, right? All right, and then we're going to have one more step. And this is going to be catalyzed by an ER, which is an enol reductase, which is once again going to use NADPH, and that is going to reduce alright, and then you're going to end up with a saturated fatty acyl chain stuck on the end of your ACP. And that will look like this. Well, just trust me, it's an ACP. Alright, now this is going to re-enter this cycle, and then it's going to go around in circles about 6 times until it reaches a mature fatty acid. Okay, and so you can see here you'll have the same thing. You'll come in, you'll have this malonyl CoA will decarboxylate, and instead of attacking the CoA, it will now, why not just go ahead and say it will now I wonder if I can just select this. So these were our carbons before, right? So this now would be your 5, 6, and this would come in an attack. And then, yeah, you would end up right back here, only you would extend it by 2 carbons. And so, yeah, as you go through, you can see you'll end up in a process where you'll eventually be able to make a fatty acid. Once it gets here, it will be offloaded by an acyltransferase or a thioesterase, and then you'll end up with a fatty acid. Let's say 1, 2, 3, 9, 10, 11, 12, 13, 14, 15, 16. And just to put it into context, that will mean that your last 2 carbons here are going to be your original 1 and 2 carbons. So that means the first thing that you put on here, which was acetyl-CoA, is actually going to be the very terminal end. So this is acetyl-CoA. So what that means for you thinking about these problems is that you're going to have, kind of the backward of what you might think, meaning that the last thing that you add is actually the first front end, okay? And so you're going to need to think about that when you're doing polyketide synthases, because you're going to have a loading domain, and that's going to load the first thing, but that loading domain and the first thing it loads will actually be the very end of the polyketide chain. All right, and so that's just kind of the overview of fatty acid biosynthesis. And the reason that we've done this is because the same reactions that happen throughout fatty acid biosynthesis, so this ketosynthase, this ketoreductase, the dehydratase, and the enoyl reductase are the same enzymatic, are the same types of enzymes or domains that we're going to see in polyketide synthases. And so you can imagine if you wanted to extend this carbon chain by 2 more residues, you could go here, and then maybe you stop here, and instead go straight back here and then cycle back around. Or you could stop here and cycle back around. And in that case, you'll end up with either a keto moiety or a hydroxy moiety on your final product, instead of having a fully saturated fatty acid like we do here. All right, so with that, I think we can go ahead and start the problem. So here is our synthase. Now I will draw out what I think the product will be for each step, and then I'll try and cyclize it, and we'll see. I haven't actually looked at the answer for this, so bear with me, but I think maybe that's a good thing. You can see how I work through it, and then maybe you'll see me get stuck. All right, so the way I'm going to do this is we're going to actually draw out the product that you would get from each one of these. And so I will not be redrawing all of these domains. I'll just draw the ACP, but I'll say this is what you would have attached. We'll say loading domain. All right, and what are you going to have there? It's exactly what it says. I'm just going to put an A, and then you'll have your S. So so this is going to be propionate, right? So this means it came from propionoyl-CoA. And then what's going to happen for the next one is we have to think about this, right? So just like in fatty acid biosynthesis, you're going to have this decarboxylated clays and condensation occur. You're going to lose this carboxyl group, freeing up some nice electrons to come in and attack this carbonyl group, and then I'll spare you all the mechanistic details, but that'll end up collapsing and offloading this thioester, and then what you'll end up forming on the second one, so we'll say on module 1, your ACP or whatever. I'll write ACP. I don't want to confuse people. In this case, is going to have your S, right? And then it's methylmalonyl-CoA. And before we say what this carbon is, we have to look at what these different domains are going to do. All right. So this AT loads a malonate or methylmalonate, which then makes methylmalonyl ACP. That will condense with this propionyl ACP over here, and then this keto reductase will modify whatever's at the beta position, which will be this guy. And so for the first one, I'll kind of show you what the product is, and then we'll go through the modification. And for the next ones, I'm not going to go in detail, but you should be able to get the point. So we'll do module 1 as 2 steps. So here, you're going to end up with this beta keto group, right? So here's your propionate that's now been attached to your methylmalonate. Ooh, that's all I want to do. All right, and then the Kr in this domain is going to reduce via NADPH, just like we saw before. It's going to reduce this ketone. Right, so then you'll have nothing's changed there, but now you're going to have this guy. Alrighty, so now you can see what we have for module 1. So let's go ahead and move on, and maybe I can make this a bit bigger for you guys. And then yeah, let's go ahead and say this is alright, so let's go into module 2 then. Alright, so I'm not going to show what these do now. You should have the general idea that once you have done the condensation reaction, in this case, catalyzed by this ketosynthase here, this keto reductase will act selectively on the beta position, reducing that carbonyl down to the hydroxyl group. Just like we saw in fatty acid biosynthesis, all of the action happens at the beta position. Alright, so alright, let's go ahead and do a module 2. Alright, let's draw our ACB. And once again, we got to look at this guy. So we have malonyl-CoA instead of methylmalonyl-CoA. So that means that you're going to have... Sorry, guys. Yeah, there's a road outside of my house, so I have to deal with that. This is malonyl, so I'm just going to leave it like that. Now I got to think what's going to happen to this beta position. Right, so I have here a dehydratase and a keto reductase. That means I'm going to reduce it, so I'll end up with a similar situation I have here, but then I'm going to eliminate it. And I'm going to eliminate it to make the conjugated alpha-beta unsaturated ketone. So don't eliminate backwards, you want to eliminate towards the carbonyl, because in that case, you have a pi system that's stabilized. So just think about it in terms of just your general organic chemistry. The more stable product will be to dehydrate here, and in that case, you have this conjugated pi system. You can form, anyway, you get the point. All right, so let's go ahead and then say, so what we'll do is we're going to put a double bond here. All right. Now this was our last carbon before with the methyl group. And then here we go. And then we're going to have the OH. So this is from our our propionate on the back end. So 1, 2, 3, if you want to just make sure you're going to have an extra carbon hanging off here on the end. All right, so it's module 2. So what are we going to have on module 3? And yeah, I'm going to start having to run out of space here. But all right, module 3 is your favorite module. Module 3 has just a KS, an AT, and an ACP. And so this is not going to reduce anything. So it is the least amount of thinking you have to do. So, and then take note that it will load methylmalonyl-CoA. So here we go. I will draw some ACP action with the correct color. You're always going to have a nice thioester at the front. In this case, you have methylmalonyl-CoA, so don't forget your methyl group. All right, and then you're going to have a ketone because you have no modifying enzymes. It's just the KS, the AT, and the ACP. All right, so then you can go to your next one. Remember, we had our double bond there. You can see that right there. So this one was a methylmalonyl-CoA. And that was your propionate. All right, cool. So we're moving along. Let's go and zoom out here for a second. Come back. So that was module 3. So we have another one here. This is this pink one. This is module 4. So it has a KS, an AT, a ketoreductase, a dehydratase, an enoreductase, and an ACP. So this is basically a fatty acid synthase. But instead of acting iteratively, it's only going to work once. Sorry about the train. All right, so with that, just take note that it's going to load methylmalonyl-CoA. So the first thing that we're going to draw here is going to be methylmalonyl-CoA. Have your thioester. It's methylmalonyl-CoA, so you're gonna need that guy right there. And then because you have all of the modifying enzymes, you're going to just leave this position blank. It's the methylene, all right? And then you have to build what you had before. So remember our previous guy over here was a methylmalonyl-CoA, so you put that one in. It also didn't reduce this position, so you're going to put this here, so just moving down, and then you have your alkene here, but it was from a malonate, so you have no methyl group. Then you're gonna have your methylmalonyl-CoA here, and then your propionate loading domain. Bam. All right, so alright, so then you have a very similar situation to what you had at the beginning, right? So you're just going to have the KS, the AT, the KR, and the ACP, so that's going to make a hydroxyl group, right? So this is going to be your module 5. Alright. Let's see if I can just go here. Alright, I'm going to cheat a little bit, so I don't know if I can do this, but I'm going to try. Nice. Okay, so the module 5, like I said, is going to add once again, you had methylmalonyl-CoA, so you have this position is that, and then you have your OH. All right, and then there's just one more, and I think I can do this with the space I have, module 6. I'll draw this one out, I just couldn't see it over there, so I figured that would be easier. ACP. Let's go check out what we have. All right, so the last one, module 6, is over here, and you can see that KSAT-ACP. All right, so in this case, all we need to do is add a keto group, and then we have to worry about this TE at the end. Alrighty, so let's go ahead and do that. It's going to get kind of long, and my handwriting is terrible, so let's see how we do it. Correct color, please. Nope, I'm sorry, I forgot to see. Is it methylmalonyl-CoA? It is methylmalonyl-CoA, so make sure what your extender unit is. All right, and then I have no modifying domains, so it's going to be something like that. It's going to have a nice ketone, and then we're going to build the rest of this, right? So right, this guy is this one, right? Right, so that means that you have your methyl group here. You have an OH. Methylene, because you had all of the modifying enzymes there. And we're back to our loading domain. Propionate. Bam. Alrighty, so then you have a TE. So this all gets technically transferred onto the OH of this, but we will not talk about it that way. We'll think about it, yeah, why not? Alright, let's see if I can grab this whole guy. It's too much. Alright, sorry about that. Alright, so you have something like this here, and then what this TE is going to do is going to take this OH group, probably at the terminus, in the sense of these are what we're going to classically see, these macrolactones, and then it's going to cyclize this polyketide product. Alright, so I went ahead and numbered this carbon chain. So if we are going to cyclize, we're going to cyclize, like I said, from this hydroxyl group. That'll make a lactone and offload from this TE. So I numbered just from the carbons. This really be a 14-membered ring, but I've numbered 13 carbons, and I've drawn a 14-membered macrocycle here. with the oxygen here at the 14th position, and then numbering 1 all the way around to 13. Alright, so now that we have the basic scaffold of the polyketide build, we can start to put in our missing pieces. And so the 1 corresponds to the 1 here, and that's going to be, so the 1 here corresponds to the 1 here. So that is going to be the propanoyl-CoA that was put on by the loading domain originally. So we're going to have an ethyl group hanging off there. All right, and that means that at every odd position, you're going to be where the ketone was from either your malonate or methylmalonate. So we'll go through. So you'll have your even positions 2, 4, 6, so on, going to be where you have methyl groups if you have methylmalonyl-CoA, and it'll be a methylene if it was malonyl-CoA. So for the 2 position, you definitely have a methyl group here. Hang on. And then for the 3 position, you can see we have an unsaturation there. So the 3, 4 position has the unsaturation. That was malonyl-CoA, so there's no methyl group. Then we go to the 5 position. There is a ketone, so no reduction occurred at that position. Then you have 6, so it was methylmalonyl-CoA that did the condensation. Then you have the 7 position here, and this is fully reduced, so we don't do anything at the 7 position, but the 8 is going to get a methyl group. And then the 9 position is an OH. We get enough. All right, and then the 10 position, once again you have a methyl group sticking off there. The 11th position is an unreduced ketone, and the 12th position is a methyl group. All right, and so I had already written it, but this is basically the structure for picromycin. So we can bring that in here. Let's see. Where did it put it? Nice. All right, well, it's not as big as I thought it would be, but anyway. There's picromycin. Let's zoom in on it. So you can see this is the same thing we just drew here. There are some differences though, so these things are modified. So this is the A glycone, so you can see that you afterwards get a sugar added on here. And I believe the only other modification is this methyl group, which is added on afterwards. So there you have it. This is kind of how you'll deconstruct something like this on a test. Or if you're interested in looking at any of the research out there or trying to figure out, what an unknown type 1 polyketide synthase gene makes, this is the process you would go through to get a first guess at that. All right, so I went ahead and brought picromycin in here to kind of compare, and you can see it's generally the same structures here. You see the 3-4 position, you see the double bond, but there's some things that are missing. So I've drawn here what would be considered the A glycone. So as you can see, I'll zoom in. There is a sugar group that's attached after the biosynthesis, this guy here, right? And then there's one other modification that I can note, and that is that this hydroxyl group is installed presumably by a P450, but to be honest, I don't know exactly how that's put in place, but it isn't put in place by the central polyketide synthase that we were analyzing here. All right, so well, there you have it. If you have a question that's similar to something like this, and you're showing a biosynthetic pathway, this is the general logic you need to go through to build it. Or if you're interested in just looking at some gene clusters on your own and figuring out what they make, this is some of the thoughts that you would go through. So with that, yeah, that's it for this problem. All right, so we just went over how to draw the product from a polyketide synthase pathway. And so you can think that if you can figure out how to draw the molecule given the modules and their organization, you might be able to develop something that represents a molecule after it's been made. So you should be able to deconstruct a product and figure out its biosynthetic pathway. And so here we have methomycin, and I'm going to go ahead and zoom in here So if you are asked or just interested in understanding how something like this is made, the first thing you need to do is kind of take stock of what you have. And what we have here, as we saw before, was a macrolactone. And so before you can start to assign where the modules, or what the modules are and what they contain, you're going to have to break this macrolactone ring. And the reason you do that is because this is how the synthase terminates the biosynthesis. So this methylmalonyl group here is the last unit added, and then that is then offloaded from a thioesterase as this hydroxyl group attacks it. So this is the final thing that was added, and this was the first thing that was added. So this is where your loading domain did some work here. So once you have that cut, you can start to figure out what the linear relationship is to the polyketide, which then allows you to figure out what the biosynthesis is. One other thing to consider when you're looking at these problems is trying to find the pattern of the the ketones or the methyl groups so that you can figure out what the units are. So you don't want to be off a carbon. So what you'll do first is you're going to number stuff. So here's your 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. All right, so you have 11 carbons in this ring, and of course a 12th member here is this oxygen from the lactone. And so the first thing that I like to do is think about, well, what am I expecting from this biosynthetic pathway? So I know I have a loading domain, so I will have to have a loading domain. And once I take stock of that, I have a loading domain, and the loading domain is going to load this guy right here. Alright, so if I take into account this loading domain, that means I have 10 other carbons, which means I'm going to have 5 modules, because each module is going to install 2 carbon units. So 5 modules. And then the last thing I'm going to have is a thioesterase, because I need something to cyclize and offload this product. Alright, so that's kind of the basics of what you want to think about, so we can go ahead and start to figure out the protein or enzymes that would be able to produce this. So as I said, I've already highlighted this as a loading domain, right? So this is just like we saw before. We have propionyl-CoA coming, so you have your ethyl group hanging off, and then there's your carbonyl. So let's go ahead and write out our loading domain setup. Here I'm actually just going to say loading, save some space. Alright, so we're going to have an AT, and then we're going to have our ACP. Alright, and this AT here is going to load this ACP with propionyl-CoA. Alright, so we've taken care of that. So let's go ahead and write out for module 1. This is our loading domain. Alright, so then after that you'll realize that the odd carbons are going to be your carbonyl carbons, and then the even carbons are going to be your methyl carbons that formed the bonds to the previous carbonyl. So in this case, this is our loading. We need to circle 2 more carbons. And sorry, I forgot to say it. You need to make sure that you look for any post-translational, or not post-translational, so post-biosynthetic modifications. So here you have this OH here. That might confuse you, but this OH is actually added after the molecule has been synthesized. So this macrolactone is made, then the OH is installed by probably a P450. So in this case, try to ignore that because actually this 3 carbon is where the carbonyl is. And so what we need to do so we can figure out what module 1 has is first we're going to look at what was the unit that the AT loaded. And in this case, you can see at the 2 position, it has a methyl group. So that means that the acyltransferase of module 1 selects for and loads methylmalonyl-CoA. Alright, so that's the first thing you're going to look at. You're going to say, okay, what does the AT load? In this case, it's going to be M-CoA, methylmalonyl-CoA. And then what you want to do is not look at the piece here, right? So this is going to be, say, M1. What you want to look at is what happened behind it, all right? So all of the modifications happen at the beta carbon. And so you can see here, this beta carbon had to have been reduced to an alcohol so that it could have ever made this lactone. So that means that you're going to have an acyltransferase that loads methylmalonyl-CoA, and then a ketoreductase that reduces the ketone from the previous loading module. And so now we can go ahead and write out what we have. So we're going to have a very not circular AT. Okay. You're going to have a KS. A KR. And an ACP. All right, so all of them are always going to have an AT and a KS and an ACP, but as we've seen, some of them are going to include some modifying domains, in this case a ketoreductase. And so that is going to give us an ACP that's slightly prettier. It's pretty ugly as it stands. So, all right, well, it's a methyl group. All right, so it's going to give us an ACP hanging on to a methylmalonyl-CoA. All right, so now you have module 1 figured out. So let's go on to module 2. So let's go back to our macrolide here and outline what looks to be the carbons installed by module 2. All right, so we're going to get the 4 and the 5. So module 2. All right, and we're going to look at the 4 position here, and the 4 position does not have a methyl group, which means that module 2's AT selects and loads for malonyl-CoA. So let's say it's going to get M-CoA. All right, and then we're going to look at the position at the 3 here. We're going to look at what happened to the preceding carbonyl group. And as you can see, we have this unsaturation here, which means that the 3 position here, which is a carbonyl from the previous module, was reduced and then dehydrated to form this alpha-beta unsaturated ketone. All right, so then we're going to go back to our module 2. And so we know it's going to select for, so there's trains that are outside our house, so bear with me. All right, so you have your AT, your KS, and then here we're going to have a KR because we're going to reduce the previous ketone, and then we're going to dehydrate it. So you'll have a dehydratase, and then you'll have your ACP, and then hanging off that ACP, we will draw our malonyl-CoA. Alrighty, so we're moving along. So we have modules 1 and 2 done, as well as the loading module. So let's continue. Alright, so you're going to circle your next pair of 2 carbon units. It's going to be carbon 6 and 7. All right, and so we're going to notice the first thing we're going to look at is what does the acyltransferase of module 3 select for? In this case, there's a methyl group, so it selects for methylmalonyl-CoA. And then we're going to look at the adjacent. Here, let's just go ahead and write that. M-CoA. And then we're going to look at this guy here, and we'll notice that the previous keto group is not reduced at all. So that means that we have the minimal form of the domain. So let's go ahead and add that and zoom out for a second. So module 3. All right, and this is going to have your AT, your KS, and an ACP, and that's it. So because the previous ketone isn't reduced, that means that there were no modifying enzymes to do that reduction, at least that we know of. So to the best of our knowledge, that's what we have. And so we'll go ahead and draw our ACP loaded with methylmalonyl-CoA. All right, so it's our module 3. All right, we're getting close here, so then we're going to go ahead and circle the next 2 carbons. So the 8 and 9, once again, the first thing we're going to do is we're going to look here, and we are going to see that it is a methyl group, so that means that what we have is module 4 will load a methylmalonyl-CoA. And if you look at the previous carbonyl group, which is number 7 here, it's a methylene, which means that you had the full suite of modifying enzymes present in module 4. So let's go ahead and add those. Always forgetting to change. All right. Module 4. All right, so you're going to have AT, your KS, KR, DH, ER, and then your ACP. All right, and so as we said, it loads methylmalonyl-CoA, so let's draw one of those. And then there you go. All right, so then I'll just go ahead and write it out. So now we have module 5. This will be our last module for the thioesterase. And that's going to be your carbons 10 and 11. So let's go ahead and circle them for good measure. Make sure we have everything accounted for. There we go. All right, so once again, the first thing we're going to note is that module 5 selects and loads for methylmalonyl-CoA. So you have another M-CoA. And once again, we're going to look at the previous position. So this 9 position is a hydroxyl group, which means that the ketone had to get reduced to the hydroxyl group. So once again, we have a module that has the AT, KS, KR, and ACP. And it selects and loads for methylmalonyl-CoA. AT, KS, KR, ACP, Alright, and then the last thing you're going to have is going to be a TE. So don't forget your TE. If you don't have a TE, you don't form the macrolactone, so then you don't form the product, which means the biosynthesis is incorrect. So don't forget your TE. Otherwise, that is basically how you'll walk through looking at these polyketides to figure out how they're made. The type 1 polyketides are really nice in that sense that you can really deconstruct what made them, or if you have the biosynthetic pathway, as we previously saw, you can draw out what the potential molecule might be. And all right, other than that, that's pretty much what you need to know for these PKS problems. But like I said, if you have any issues, feel free to shoot me an email, and I'll do my best to clear up any problems you might have.